Hey guys, Mr. B here, and in this video we're going to be going through the practice problems in chapter 5.3. So let's begin here with number 1. It says, what is the frequency of radiation with a wavelength of 5.00 times 10 to the negative 8th meters? In what region of the electromagnetic spectrum is this radiation? Okay, so to answer this question, we are going to need to use the equation from the chapter, which is the speed of light, c, is equal to wavelength, which again is lambda. So let's insert special character lambda and also special character nu. Okay, so speed of light is equal to wavelength times frequency. This question is asking what is the frequency of radiation with a wavelength of 5.00 times 10 to the negative 8th. So if we rearrange this equation, so we have wavelength is equal to this is going to be speed of light divided by lambda. This is what we get. Okay, so we're trying to solve for frequency. So we're going to have frequency is equal to speed of light, which is 3.0 times 10 to the 8th meters per second. I think in the chapter it was 2.998. So we'll use what's in the chapter, but it's the same thing. It's fine. So 2.8 times 10 to the 8th meters per second divided by wavelength, which they're giving to us in the problem, which is 5.00 times 10 to the 8th, I'm sorry, to the negative 8th meters equals, so let's do this out on a calculator and figure out what we have. So we have 2.998 times 10 to the 8th divided by 5.00 times 10 to the negative 8th equals, all right, so we have a really big number, and I'm going to write it down below here. So we have 5 point, I'm going to do this in, well, I guess, sorry, we'll write it out normal, and then we'll put it in scientific notation. So 996, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This will be in hertz, okay? So this is our number. This is our frequency. Let's put this in scientific notation, though, because it's kind of weird to work with this giant number. So in scientific notation, it's going to be 5.996 times 10, and it's going to be to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times 10 to the 15th hertz. Okay, so this is our better answer. So this is our frequency. In what region of the electromagnetic spectrum is this radiation? So let's go back in the chapter and find our electromagnetic spectrum picture, which is up here. So our answer is 5.996 times 10 to the 15th. So if we look here on our electromagnetic spectrum, if we zoom in, well, I guess, yeah, let's go view, zoom. So times 10 to the 15th is going to be, so here's to the 14th. Here's the 16th is ultraviolet. So 10 to the 15th is probably somewhere right in the middle, which would be in the ultraviolet range. Okay, this is going to be in the ultraviolet range of the electromagnetic spectrum, which is going to be our answer here. So in what region of the electromagnetic spectrum is this radiation? We can say this would be in the ultraviolet range. Okay, be in the ultraviolet range. All right, let's unzoom here. Number 2, true or false? The speed of light is a constant that can be obtained by dividing the frequency of light by its wavelength. So this is false, because we have the equation right here. The speed of light is going to be obtained by taking the wavelength times the frequency, not taking the frequency divided by wavelength. So this is false. And if we can select the right part we want here, there we go. This is false. Number 3, true or false? The amplitude of a wave is the distance between the crests. So again, let's go look back at our notes. And the amplitude is the height from the base to the crest. The distance between crests is the wavelength. Okay, so the wavelength is the distance between crests. Amplitude is the wave's height from 0 to the crest. So that is also false. That is not correct. So false. All right, number 4. What is the wavelength of the radiation whose frequency is 5.0 times 10 to the 15th inverse seconds? In what region of the electromagnetic spectrum is this radiation? Okay, so it's basically same as like question number 1. We have our equation, which is speed of light is equal to, insert special character, lambda and nu. Okay, so we have speed of light is equal to lambda times nu. Now they're asking for wavelength, which basically then is going to be lambda is equal to the speed of light divided by frequency. Okay, like this. So our lambda is going to be equal to 2.998 times 10 to the 8th meters per second. So that's the speed of light. Divided by the frequency, which they are giving to us in the problem, which is 5.00 times 10 to the 15th inverse seconds, or we're just going to write hertz, okay? And all we have to do is just put this in a calculator and basically get an answer. So let's just copy paste this down here. Okay, so wavelength is equal to, all right, so let's do this out on our calculator. 2.998 times 10 to the 8th divided by 5.00 times 10 to the 15th equals, and we get a very small number, but we get 0. So let's see here. 1, 2, 3, 4, 5, 6, 7. I'm just going to double check that. 1, 2, 3, 4, 5, 6, 7. Yep, 5996 meters. So that is our wavelength, which let's put this in scientific notation. So this is going to be 5.996 times 10 to the, and let's see, we're going to move this over 1, 2, 3, 4, 5, 6, 7, 8 places. So 10 to the negative 8th. Oh, all right, whatever. Negative 8th meters. There we go. Okay, so that is our wavelength. And what region of the electromagnetic spectrum is this? So again, let's go back to our picture. And we're looking for times 10 to the negative 8th. Wavelength is down here at the bottom, so let's zoom in on this. And times 10 to the negative 8th is right here. So again, that is going to be in the ultraviolet range. So that is the answer we are going to give them. Again, let's unzoom. So this would be the ultraviolet range. There we go. All right, number 5, list the colors of the visible spectrum in order of increasing wavelength. So this is going from small wavelength to high wavelength. So let's go back again to our chart. Let's zoom in on this one more time. We're going to be looking at this a lot, by the way. So low wavelength or small wavelength is 380 nanometers. That's small wavelength. And large wavelength is 700 nanometers, right? That's bigger. So the colors of the rainbow from low wavelength to high wavelength are violet, indigo, green, yellow, orange, red. Or Roy G. Biv, but just backwards. So we will go with, let's change our color here. Here we go. So Roy G. Biv. Okay, that is our rainbow colors, but the other way around. So we're going to have violet, indigo, blue, green, yellow, orange, and red. Okay. So increasing wavelength. So violet, let's actually make this smaller font. So this is going to be smallest wavelength, and red is going to be largest wavelength. And we'll underline this here just so it stands out a bit more. There we go. Okay. And let's maybe make this font just a little bit smaller so it maybe all fits in one line. There we go. Okay, so smallest wavelength to largest, those are the colors. All right, number 6. Let's zoom back out again. Consider the following regions of the electromagnetic spectrum. So ultraviolet, X-ray, visible, infrared, radio wave, microwave, okay? Use figure 5.10 to arrange them in order of decreasing wavelength. So I think figure 5.10 is this picture, okay? So we are going to order those in decreasing wavelengths. That means from largest wavelength to smallest wavelength. So let's, again, go look at our picture. And let's see here. So largest wavelength is, I think, on the left. So that's going to be radio waves, then microwaves, then infrared, then visible, then ultraviolet, then X-ray. All right, so let's go again, look at our answers. And the decreasing wavelength will be, and let's change our font size again. Let's go 18. So we're going to have largest wavelength is radio waves. Then we have microwaves. Then we have infrared. Then we have visible. Then we have ultraviolet. And then lastly, we have X-ray. So this is from... Okay, that's not what we want. This is from largest to smallest. There we go. Okay. Letter B, how does this order differ from that of decreasing frequency? Okay, so let's take a look at decreasing frequency. And if I remember right, remember that frequency and wavelength are inverse. So basically decreasing frequency would be opposite. So largest wavelength is down here and smallest wavelength is down here, but smallest frequency is down here and largest frequency is down here. So basically how it differs is it's opposite, okay? So largest wavelength is going to be smallest frequency. Smallest wavelength is going to be largest frequency because remember, they're inversely proportional. So let's unzoom. How does this differ? We'll say that largest wavelength is equal to smallest frequency. And smallest wavelength is equal to largest frequency. Okay, so again, they're opposite from each other. So can we do this maybe? There we go. Yeah, anyway. Okay, that's fine. Okay, number 7. The transition of electrons from higher energy levels to the n equals 2 energy level results in the emission of light from hydrogen atoms. In what part of the spectrum is the emitted light, and what is the name given to the transition series, or given to this transition series? All right, so this question, in order to answer this question, they're basically saying when electrons go from higher energy levels and they drop to the second energy level for hydrogen atoms, what part of the spectrum is this light in, and what's the name of that series? And that's actually going to come from this picture right here. Okay, so we're going to zoom in on this. So this shows that when we have electrons from hydrogen and they go from high energy level and they drop to the second energy level here. Okay, so the second circle. That's this section of the spectrum right here. So this is known as the Balmer series, and this is going to be in the visible light range. So that is the answer for this question. So it's, again, what part of the spectrum is the emitted light, and what is the name given to the transition series? So this is going to be in the visible light range. So in the visible light range, and it is known as the Balmer series. All right, and then last question, explain the difference between the energy lost or gained by an atom according to the laws of classical physics and according to the quantum mechanical model of an atom. So basically, this one is kind of hard to get from the chapter section and reading it, but the difference between energy lost or gained in regular physics compared to quantum mechanics is, in regular physics, energy is continuously lost. So energy is like lost or gained all the time. And in quantum mechanics, energy is lost in a very finite amount. You lose this much, right? You don't, like, it's quantum, it's quantized, so you have to have a very specific amount. So in quantum mechanics, energy is lost in a very specific amount known as a quantum. All right, so that is it for this section notes. That was the last one. I know that these questions took a little bit, and there's a lot of heavy vocabulary and stuff, but Hopefully that makes sense. If you have any questions, though, make sure that you reach out to me so that I can help you, okay? All right, guys, that's it for this one. I'm Mr. B. Thanks for watching. See you in the next one. Bye.